Hi everyone, welcome to part 2 of Calculus Lesson 1-8 Continuity. In this video, we're going to start off by talking about combinations of continuous functions. This first theorem just lets us say that if f and g are continuous, then if I add them together, the result is going to be continuous. If I subtract them, the result is still going to be continuous. If I multiply by a constant, I'm still going to get a continuous function. If I multiply the two functions together, they're still going to be continuous. And if I divide them, as long as g of a number does not equal 0, then it's still going to be continuous. Okay, so we have some more theorems that we're going to look at to find out values where certain types of functions are continuous. If you're given a polynomial function, it is always continuous on all real numbers. So on the interval negative infinity to positive infinity, a polynomial will be continuous. A rational function is continuous wherever it's defined on its domain. If there's a value that's not in its domain, it will not be continuous for that one value. Otherwise, it will be continuous. The following functions are continuous at every number, again, in their domains. Polynomial function domains are all real numbers. Rational functions, the domain is anything that would not make the denominator 0. Root functions, remember, you want to avoid doing the square root of a negative number or any even numbered root of a negative number. So that's where those would be undefined. And trig functions, sine and cosine, are their domains are all real numbers. Tangent and cotangent would have different domains. So you'd want to just check their domains to see where it's not going to be continuous. Okay, so let's take a look at an example where we have to find out where a function is continuous and where it is not continuous. In example 5, we're going to use continuity to determine if we can actually find a limit. So it says find the limit as x approaches -2 of this function. Now notice this is a rational function. So according to continuity, we can find this limit as long as -2 is actually in the domain. So find the domain of this. If -2 is actually in the domain, then go ahead and find the limit. Okay, so this is a rational function. The domain is that x does not equal 5/3 because that would make this denominator 0. So -2 is in the domain. That means I can just take -2 and put it in for all of my x values and find the limit. So I'm allowed to use direct substitution, and I find out that the limit is -1/11. Let's take a look at some more examples where we're using continuity with limits. In example 6, they want to know the intervals that will make each function continuous. Okay, so we can limit the interval so that the function will be continuous. So take a look at each of these 3 functions and see if you can find out where they're continuous. Now, I'd just like to point out in part C, this is a sum of 3 different functions. So look at them separately, each part separately. Find the domain of each part, then put it all together into one big domain. Okay, so continuity and domain are definitely linked. So my first function is a polynomial function, which means its domain is all real numbers. So it is continuous on all real numbers, and they asked for an interval, so I gave it from -infinity to infinity, and that is my answer. In part B, I noticed that it's undefined when x is positive or -1, because if I put +1 in here, I'm going to get 0 in the denominator. If I put -1 in here, I will also get 0 in the denominator. So I need to exclude those from my domain. And they asked for an interval, so I can't just write this. I have to give it in an interval. So -infinity to -1, not including -1. -1 to positive infinity, +1, again, not including -1 and +1, and then +1 to positive infinity, again, not including +1. Now in part C, they gave me a sum of functions, so I'm going to look at each function individually for their domain, and then I'm going to use that to build my interval. The square root function has a domain that x has to be greater than or equal to 0, because I can't do the square root of a negative number, but I can do the square root of a 0 or a positive number. For this part, this rational function here, x can't be 1, because that would make the denominator 0. And for this function, there is no limit to my domain here, because if x is a -1, it's going to square and become positive. If x is +1, it's going to square and become positive. There's nothing that will make this denominator 0 as far as real numbers are concerned. Imaginary numbers, that's a different story, but we don't look at those for domain and continuous. So when we combine the two limited values for our domain, we find out that we can include 0 all the way up to 1. 1 is not included because it says x can't be 1. And then from 1 to positive infinity. And that is the interval on which this function is continuous. Okay, let's take a look at another example. So in example 7, they want us to evaluate this limit, but first we should make sure that it is continuous, and then we can evaluate the limit. So the first thing you're going to do is determine when sine x is continuous and when 2 plus cosine x is continuous. Be careful about that denominator equaling 0, and then determine if you can find this limit and actually do it if you can. So pause the video, see if you can do that, and then press play to check your answer. Okay, so this is a combination of two functions. Sine x is always continuous on the domain of all real numbers. 2 plus cosine x is a sum of continuous functions. 2 is continuous, cosine x is continuous, and this domain, again, is all real numbers, because cosine x has a domain of all real numbers. 2 is just a constant value. Again, the domain is going to be all real numbers. Now, the only place where we might have trouble is if that denominator equals 0. But remember, cosine x can only output values from -1 to 1. So even if this was a -1, 2 plus -1 is going to be more than 0. It's never actually going to hit 0 because we're adding 2 to it. So it's impossible for that denominator to equal 0. So this function is continuous, and we're allowed to use substitution. So I'm just going to put in pi for this. Sine at pi is 0. Cosine at pi is 1. So I get 0 over 2 minus 1, which is 0. Okay, now let's take a look at continuity with composite functions. So the first theorem we have about composite functions is that if f is continuous at b and the limit as x approaches a, g of x is b, then the limit as x approaches a, f of g of x is f of b, which sounds really crazy. But basically what that's telling us is that if we have continuity happening, okay, I can do the limit of the inside function, find that value, and then just plug it into my f function. That's all it means. Okay, so if I have a composition of functions, I can find the limit of the inside function, then take that value and plug it into my f function, my outside function. Okay, so it can help us if we recognize a composite function. We can just do the limit of the inside and then evaluate. The next theorem says if g is continuous at a and f is continuous at all values of g of x, then the composite function f of g is continuous at a. So a continuous function of a continuous function is a continuous function. So when I do composition of functions, as long as my outside function and my inside function are both continuous, then the resulting function is also continuous. Okay, I know those are a bit confusing. Make sure you ask me if you have questions about them. Let's take a look at an example though. In example 8, we're asked to determine where the following functions are continuous. So notice these are composite functions. In part A, we have this x squared inside of a sine x. Okay, in part B, we have several compositions happening here. So there are several functions going on in part B. Remember, we find the domains of all of these functions, and then we see what they are, and we check to see if we have any conflicting things, and we can write our continuity based on the domains. So try it out, and then press play to check your answer against mine. In part A, the inside function is continuous on every real number, and the outside function is continuous for every real number. So this is continuous for every real number. So it is always continuous. Now in part B, this is a composition of 4 different functions. We have 1 over x. We have x minus 4. We have the square root of x, and we have x squared plus 7. So all of that is happening, but the important part is to find the domain of this entire composite function. Now, that would just be checking to see where this denominator is 0. And the denominator is 0 when x is positive or negative 3. Because if it's 3, then I'll have 9 plus 7 is 16. The square root of 16 is 4. And 4 minus 4 is 0. Okay, so positive and negative 3 are not included in the domain, which means that this is the interval of continuity. Negative infinity to negative 3, negative 3 to 3, and 3 to infinity. All of those are not including the negative 3 or the 3. Now, I know this video is a little long, but we have one last thing to talk about. Here it is. The intermediate value theorem. It says, suppose that f is continuous on the closed interval a to b. Let n be any number between f of a and f of b, where f of a does not equal f of b. There exists a number c in a to b such that f of c equals n. Okay, this is just a very fancy way of saying that as long as my function is continuous from a to b, then I can pick any number between where I evaluate them to get, any number between there, n, okay? And there's going to be a number between a and b that will get me that n value. Now, it's really useful to use this to find zeros, because if f of a is negative and f of b is positive, then there has to be a 0 in between those two numbers, because it's continuous. It can't skip over the 0. And that's what this is talking about. It's saying if I have a positive value here and a negative value there, and it's continuous in between, then there has to be a 0 in between. And this is saying if I have like 16 up here and 5 right here, and I say 10 is in between, then there has to be a number over here, c, that's going to give me 10 when I put it in. That's what it's saying. So let's take a look at an example. In example 9, it asks you to show that there is a root of the equation between 1 and 2. So basically, evaluate for 1, evaluate for 2, show that one's positive, one's negative, and there must be a 0 in between. So go ahead and do that, then press play to check your answer. When I evaluated for 1, I got negative 1. When I evaluated for 2, I got 12. This is a polynomial function. It is always continuous, which means that because the intermediate value theorem will apply, and I got a negative number and a positive number, there must be a 0 in between them. Okay, so that's it for this video. Make sure you let me know if you have any questions, and don't forget to do your homework.